So, in this session we will be going to discuss about the design technique of shell and tube heat exchanger. However, you see, to design this exchanger there are multiple process variables to be considered, and this includes you see the dart factor, and as we have mentioned that in multi-pass heat exchanger the flow pattern or the contacting pattern changes from one pass to another pass. Like in a 1 2 pass shell and tube heat exchanger, where we have two tube passes and one shell pass, and we can have this fast co-current then counter current contacting pattern, or alternatively we can also have fast counter current then co-current contacting pattern. And because of this shift of this cross flow to counter flow from one pass to another pass, we have to introduce a correction factor, right, in the overall heat transfer coefficient, and that is called, or rather in this log mean temperature difference correction we have to do for it in order to actually get this correct capacity equation, right. So, you see that here we are going to discuss some process consideration for thermal design of shell and tube heat exchanger. So, first the unique parameter which comes in this picture, and it is unique to shell and tube heat exchanger only, it is not at all valid for double pipe, and specifically it originates from this multiple passes, right, and that is the log mean temperature difference correction factor. Additionally to this U we have the dart factor, right, which is to be included in the clean overall heat transfer coefficient in order to get the design overall heat transfer coefficient. Additionally, there are considerations regarding the heat transfer coefficients itself, individual film heat transfer coefficient HI and HO, how to calculate the tube side and shell side heat transfer coefficient. And specifically tube side it is pretty simple, but complication comes in shell, right, because in the shell, because of the baffles we have this cross flow type of flow contact, or where the tube fluid moves like horizontal or vertical, where the shell fluid follows a zigzag pattern. So, how to calculate this shell side heat transfer coefficient, that we are going to discuss. And finally, before we discuss about the design, we have to know the pressure drop calculations, right. So, we will start with this log mean temperature difference correction factor and this fouling factor. So, first one is the log mean temperature difference, that is LMTD. In short, it is also referred as LMTD correction factor. Represented as FT, right. So, to understand this, let us have a 1 2 shell and tube heat exchanger. So, you see, if the arrangement is something like this and we have the baffles here and we have the tube side inlet here tube side outlet here. So the shell fluid will move like this. So let's say this, in the shell we have the hot fluid TH1 and this is TH2, right? Okay, in the shell we have the cold fluid, say it is TC1, this is TC2, right? And in the tube we have the hot fluid, right? So we have the tubes like this. So the tube side fluid enters at temperature T1, TH1, so it will move like this and move out at a temperature of TH2. Generally, it is recommended that you deliver the hot fluid through the tube side. Why? Because except it is a condensing system, like steam. So why we deliver the hot fluid through the tube side? Because if it both are in the liquid phase, then generally we deliver this hot fluid through the tube side, because if we deliver in the shell side, there are chances that we will have the loss of thermal energy and we cannot optimally utilize the enthalpy in heating up the other stream, right? So that's why the hot fluid is commonly recommended that you deliver it to the tube side. Okay. Now this arrangement is called, in the first pass, the shell side fluid is moving from left to the right, the tube side fluid is also moving from left to the right, right? So the first tube pass, it's co-current as we have discussed. However, when the tube side fluid returns to the second tube pass and the shell is still moving, shell side fluid is moving from the left to the right and tube is moving from right to the left. So second tube pass is countercurrent, right? And we name this heat exchanger in order to differentiate from the other structure. We call it 1-2 co-current shell and tube heat exchanger. Why? Because in the first pass, the name has been given based on the contacting pattern in the first pass. So what is the expected qualitative temperature profile of the tube and shell side fluid, right? So the tube side fluid, the shell side fluid, its temperature, tube side what happened? This okay, anyway, the shell is cold fluid, so cold fluid temperature will increase and tube fluid temperature will decrease, right? So this is the profile, whereas for tube side fluid it decreases like this. Okay. So this is TH1, this is TH2, this is TC1, this is TC2. On the other hand, if I have an arrangement like this, see, cold fluid here we deliver through the tube side, right? I am not drawing the detail. TC1, this is TC2, and the hot fluid is delivered from this side. TH1, this is TH2, right? So, what is the expected temperature profile? So, in the tube side, as in the shell side, it is the hot fluid, and this is 1-2 counter current heat exchanger. Why it is counter current? Because the shell fluid, as it has got a one pass, it is moving from the right to the left, whereas tube fluid, its fast pass, it's this is C. The shell fluid will move like this, right. So, in the first pass it is counter current, in the second pass it is co-current. So, the hot fluid, its temperature decreases like this. So, this is TH1, this is TH2, and the cold fluid temperature increases like this. Okay, let me draw it. So, this is TH2, this is TC2, this is TC1, right. So, that is the typical 1-2 counter current shell and tube heat exchanger. However, there may be chances of getting an abnormal temperature profile, where in the second pass of this cold fluid, the temperature locally may exceed that of the hot fluid. So, in that case, we can have a temperature profile like this, right. So, in that case, here this one will be this TC2. So, local temperature or the outlet temperature of the cold fluid will be higher than the outlet temperature of the hot fluid, and this phenomena is called temperature cross, and that is not at all desirable. Now, why it happens? This is abnormal phenomenon, and which can happen in 1-2 counter current heat exchanger, or at least when in the first pass, when this contacting patterns, it is counter current. So, you see that actually the linear velocity, if I think of this as z direction, right. So, z directional velocity of the tube side cold fluid is much higher than the z directional or the negative z directional velocity of the shell side fluid, because the path here is a straight path and here this is a zigzag path, right. Now, in the first pass, I am trying to explain qualitatively the phenomena of temperature cross. In the first pass, the cold fluid follows a counter current pathway. So, its temperature increases. Now, when it returns to the second pass, here you see this region is the hot region of shell fluid, right, and it enters into the hot region, right, and as a consequence its temperature will suddenly increase, and from here to here it reaches swiftly, because compared to that of shell fluid, as it is following a zigzag pattern. So, once it reaches here, which is relatively the lower temperature region of shell fluid, right, locally the cold fluid temperature may be higher, right, it exceeds, and once it exceeds, the direction of heat transfer changes. So, now the cold fluid in this region is delivering heat to the hot fluid, and definitely we will have a maxima, because it shoots up, attains a maxima and then decreases, and finally the maxima is never going to take place at the outlet, because the direction of heat transfer changes. So, we can have this temperature cross with maxima internal to this heat exchanger, and finally there will be a higher temperature of hot fluid to that of cold fluid. So, this gap, right, this is Tc2 minus Th2, it is called technically the temperature cross. Whereas, if this Tc2 is lower than Th2, this gap, right, is the temperature approach, which is conventional, say delta T2, that will be the temperature of this approach, which is Th2 minus Tc2. So, temperature cross, here I am trying to qualitatively explain, there are quantitative analysis of this temperature profiles and all, we are not going into that complexity. So, if we do this analysis, we will see that actually our capacity equation for multipurpose exchangers, it will no longer be Q is equal to some UD, design heat transfer coefficient, into A into LMTD, right, it is not. Rather, we will write it as UD into FT into A into LMTD. Now, FT is called this LMTD correction factor, and that can be theoretically estimated. However, we have user friendly charts of this LMTD in terms of temperature ratio and capacity ratio. Like what, so first we have to understand that what is a temperature ratio. Okay. So, you see that hot fluid, it is changing from this Th1 to Th2. So, Th1 is higher than Th2, and cold fluid, which changes from Tc1 to Tc2, Tc2 is higher than Tc1. So, temperature ratio, sorry, capacity ratio that is referred as R, it is equal to the hot fluid temperature change Th1 minus Th2 divided by Tc2 minus Tc1. So, that is R, and another is temperature ratio tau, which is the actual change of cold fluid temperature divided by the maximum possible change. Now, if the shell and tube heat exchanger is infinitely large, then the outlet temperature of this cold fluid can maximally attain the inlet temperature of this hot fluid for a perfect combination, right. So, it will be Th1 minus Tc1. So, this is called the capacity ratio. Alternatively, it some way reflects the thermal efficiency of shell and tube heat exchanger, right. Now, this Ft, as I have mentioned, there are user friendly representation of this Ft. This Ft is plotted for different values of this temperature ratio. There is a plot of Ft. So, Ft will be 1 here, say 0.9, 0.8, 0.7, etc. And here we have tau, and the graph looks like this for different values of R. Right. So, this is for a specific type of heat exchanger, let us say 1-2 shell and tube heat exchanger, right. Now, if I change this arrangement to 2-4, definitely the structure and the values and the pattern will be different. Overall, the graph pattern will be conserved, but the individual values of Ft will be changing. So, here we have understood that there are two phenomena. One is the non-ideality, that is the temperature cross, and how to calculate this Ft. There are standard curves. but these curves are not empirical curves. Remember that Ft can be analytically calculated, and once you calculate, you will see that this formula is not matching. Actually, we need a correction factor. So that's why correction factor has been included, and the correction factor in terms of some user friendly representation has been represented as a function of tau for different values of R, right. So R here is going to change, right. It decreases from, say, it is 15, then 14, then 13, in this way up to 1, right. So for different temperature ratio, we will get a series of curves representing the values of different R. So you see, that's about this LMTD correction factor, and in GATE there are several questions where this curve of Ft will be given. Recommended that once you are increasing the number of pass, right, that Ft, we should keep it as a thumb rule, should be always greater than 0.8. Ft less than 0.8 is not desirable, right. It is a thumb rule which is arising out from experience, that if we go for higher number of passes and with an Ft value for the sake of increasing this U, and if I go on increasing the number of passes, we should keep in mind that Ft should be always greater than equal to 0.8, and accordingly we have to adjust the number of passes, right. And second, it is all very well known, this dart factor, right, Rd, we have already discussed it. Now generally you see 1 by Ud is equal to 1 by Uc plus Rd, and based on whether this is a dart factor or dart resistance or overall dart resistance, you see we can have this Rdi or Rdo, right. This Rdi is equal to 1 divided by Hdi plus 1 divided by Hdo into di by do. We have discussed it. Or alternatively, this Rdo equal to 1 by Hdo plus 1 by Hdi into do by di, where di represents the ID of tubes and do represents the outer diameter of the tubes. So generally this Rd is given for, there are list in standard textbooks like in this book Heat Transfer by BKD. So here we can have these Rd values for different types of liquids and gases, like you see fuel oil, and here if I use this Rd in hour per meter squared degree Celsius by kilocalorie into 10 to the power 3, right. So fuel oil has got a value of 1.024. So then river water is a standard value, right. River water has got a value of 0.205 to 0.409. Process water, that's with hardness being partially removed, 0.205 to 0.409. Brackish water has got 0.407, 0.615. Here, for air, this is 0.102 to 0.205. So there are several ranges, and this has been given, right, in any standard textbook, where from we can fetch out this Rd value during the design of shell and tube heat exchanger. So once we have the idea of this log mean temperature difference correction factor. Let us move on to how to calculate the HI and HO, right. That means tube side and shell side heat transfer coefficient. See, second is determination of heat transfer coefficient. So, first it is HI, that is tube side heat transfer coefficient. Let N be the total number of tubes, N be the total number of tubes, and P be the number of tube passes. So, small n, there is a number of tubes per pass, it is equal to N capital N divided by P, right. So, tube side mass flow rate, let us say it is m dot T. So, mass flow rate in individual tube will be equal to m dot T divided by this small n, right, and let us call it m dot T superscript I, right. So, from here you calculate the average velocity of the tube side fluid as m dot T superscript I by pi by 4 dt square into rho T. Now, you see this tube side fluid's density is dependent on temperature, and whenever we are going to calculate, okay, let me first finish this V bar T, right. Now, the tube side Reynolds number will be V bar T into rho T into dt by mu T, and definitely it will be greater than 10 to the power 4, right. That is 10,000 where the C dot A equation will be applicable. So, from there this HI into dt divided by KT 0.027, Reynolds number to the power 0.8 into Prandtl number tube side to the power 1/3 into phi u, viscosity correction factor. So, we are using the C dot A equation, right, for turbulent flow. And we can get this HI, right, we can get this HI value. Now, you see this for Prandtl number calculation, for phi u calculations and KT and rho T etc., we need the temperature. Now, tube side fluid, it is changing from this, it may be hot, it may be cold. So, we have to go for calorific mean temperature, right, at which these properties are to be calculated. So, we can write the tube side calorific mean temperature is simply the arithmetic mean of inlet and outlet temperature. So, with that we can proceed for calculation, we can get the property values of this tube side fluid, and from there we can correctly evaluate this HI. So, that is the inside heat transfer coefficient. Okay. Next, we have to go for the shell side fluid heat transfer coefficients calculation. So, HO, shell side. Now, you see in the shell we have the baffles, and it is a non-circular geometry of this shell side passage through which the shell side fluids are moving, right. So, in order to understand that, first what we have to evaluate? This equivalent diameter of shell, that is DH, equivalent diameter of shell side rather, not shell, rather of the shell side, right. So, that DH depends on tube layout, right. That is whether it is a square pitch or a triangular pitch. Now, let us have the calculation for square pitch and triangular pitch separately. So, for square pitch, you see, as I mentioned, these tubes are arranged in square units. Like if I connect the centers by imaginary lines, we will get a square, and tube to tube center distance is the pitch, right, pitch, and that should be greater than 1.25 times the outer diameter of the tubes at least, and the gap between two successive tubes is called the clearance, C prime. So, you see, for equivalent diameter calculation, we have to use this DH is 4 into wetted area by wetted perimeter. So, for this unit of square pitch, the wetted area is this. Okay. So, 4 into the wetted area will be PT square minus this water circles multiplied by 4. So, this is one circle. So, that is pi by 4 d naught square is to be subtracted. So, that gives you the exact estimation of the hatched area. And the wetted perimeter, see, actually the solid perimeter which we are having here is this 1/4, this 1/4, 1/4 and additional 4 1/4s. So, 4 1/4s means a single tube's total perimeter, and that will be this pi d naught, right. So, that is the DH expression for square pitch. Next, if I go for triangular pitch, the structure changes, it is this. So, the unit instead of square is now forming an equilateral triangle with the side PT, because this is center to center distance, and the wetted area will be this. Okay. Wetted perimeter, this and this, where individual angle is 60 degree. So, this angle is 60, this is 60 and this is 60. So, the total angular span of this perimeter is 3 into 60, that is 180, right, and we know for 360 the perimeter coverage is pi d naught. So, for 180 it will be pi d naught by 2, right. So, DH it's equal to 4 divided by wetted area, that is pi d naught by 2. Now, the wetted perimeter, and here it is wetted area. It is the area of this equilateral triangle, and we have to subtract again the half of the cross sectional area of individual tube, right, considering its outer perimeter. But why half? Again 60, 60, 60, 180. So, 360 corresponds to pi d naught square by 4 area. So, here the area will be pi d naught square by 8, whereas the area of this equilateral triangle, when we know from the elementary formula for mensuration, root 3 by 4 PT square minus pi d naught square divided by 8. So, this is the expression for equivalent diameter with triangular pitch. Now, as we have mentioned, the square pitch gives lower delta PS and easy for shell side cleaning, or rather facilitates shell side cleaning. right? Whereas this triangular pitch higher number of tubes are accommodated. Now difficult, definitely it is difficult to clean, right? So you see that once we have got this equivalent diameter, now for HO we have the formula of Kahn proposed in 1950, which states that HO into DH divided by KS equal to 0.34 into DH into GS divided by mu S to the power 0.55 into Prandtl number to the power 1/3. Right. So let me check it once again. And definitely there will be viscosity correction factor phi u, which is mu by mu w to the power 0.14. This is an empirical equation. Now what is GS? GS is the mass velocity equivalent to average velocity into rho of shell side fluid, right, of shell fluid. Now how to calculate it? GS, definitely the mass velocity V into rho, you can understand from the dimension that it will be mass flow rate divided by area, right. So it is m dot S divided by AS. Now what is the flow area for the shell side fluid? Now you see, for that we consider the space between two successive baffles. Okay. Let us say this is a segment baffle like this, and this is also a segment baffle like this. So how the fluid will flow? Shell fluid will flow. It has to move through this space and it has to move downward, right? So here we will always go for a bit underestimation of H, right, HO, because if we overestimate HO, we will underestimate the area and that may underperform, right. So what is the maximal area? It is the mid plane area, this plane, right. And here we have tubes with an intermediate gap through which the shell fluid actually is moving up. So in projection it looks like these are the tubes, right. So this hatched area is actually the area available for the shell side fluid to flow, right. Now what is the gap between the two baffles? We know that this is equal to B, baffle spacing, right, and this gap is the clearance C prime. So individual area of the rectangle like this area is B into C prime. Now how many such rectangles are present? You see that this diameter is the shell diameter ds and tube to tube center line distance is pitch. So the number of rectangles we can fairly approximate as ds divided by pt. So AS becomes ds divided by pt, number of such rectangles into individual rectangles area. Okay. So you see here from we can get a direct quantitative relation between the baffle spacing and the HO, like GS HO becomes proportional to, so here GS in the denominator we have m dot S, so here it will be AS, right. AS is proportional to B, so HO is proportional to 1 by baffle spacing to the power 0.55, right. So this gives you the clear-cut idea that how the baffle spacing influence the shell side heat transfer coefficient. Okay? So if we increase the baffle spacing, my shell side heat transfer coefficient is going to decrease. It's obvious. So you remember this equation and the respective inference what we can draw regarding the influence of baffle spacing on HO. So, we have got the ways to calculate the shell side heat transfer coefficient, and also previously we have discussed about that how to calculate the heat transfer coefficient for the tube side fluid, right. So, next, the last important issue for process design is the pressure drop. So, for pressure drop we will simply use this Darcy's relation, okay, but with a bit of modifications of course. So, empirical modifications are included. So, you see pressure drop calculation. So, first is the tube side. We know that Darcy's law is 4FF L by D, right, tube diameter into V square divided by 2G. Maybe we are going for gravitational unit. So, we can modify it as delta PT as 4FF into L. L is a tube length, and this V bar we can replace as GT, the mass velocity through the tube, by rho T, right. So, it is all the same basically, GT square, and rho will be cross multiplied here. So, GT square divided by this will be 2, right, G, then here we will have a rho T, and dt will be there, the diameter of the tube, and the empiricity what we introduce, right, is the number of tube passes n. So, n represents here, because if there are 2 passes it is covering 2 of L. So, this is the number of tube passes, and here an empirical correction factor of the same this phi u, mu by mu w to the power this, yeah, the dimensionless viscosity ratio mu by mu w to the power 0.14. So, that is the formula for calculating the shell side tube side pressure drop. Now, so this is in tubes, and in returnments there will be some minor loss, and that you see it is k into V square divided by 2G into rho. So, delta P R in returnments, it has been proposed that if there are this basically n numbers of tube passes, it will be 4n into V squared or V bar T square divided by 2G into rho T, right. So, when n is the number of tube passes. So, the total pressure drop delta Pt will be delta P small t plus pressure drop in the returnment. So, that is for the tube side pressure drop calculation. Second, it is the shell side. So, first in the shell side we can think of unbaffled shell, which is obviously hypothetical. Right. So, here delta Ps similar to this 4 2ff L into GS square into capital N, the number of shell passes, into G rho s into this ds equivalent into phi u. Right. So, dH you see, or ds equivalent for unbaffled, it is equal to what? 4 into weighted area. Weighted area will be pi by 4 into ds square minus total number of tubes into pi by 4 d naught square, that is the area, right, divided by weighted perimeter, that is pi ds plus nt into pi d naught. So that's for unbaffled shell. Definitely we don't use unbaffled shell. So here for baffled shell, this whatever may be the number of this shell passes, actually you see for it's covering this part, right, and if it is 1 2, it will be this, okay, it will increase. So let's go for baffled shell, 1 shell pass, right. So here delta ps will be 2 ff. Now L will change, L will be ds into nb plus 1 into gs square divided by g into rho s into dh rather, the equivalent pipe diameter into phi t, whatever we have calculated. Yeah. So why it is such? ds into nb plus 1, because if there are n number of baffles, see how many baffles are there, right, this many baffles. So 1 2 3 4 5 6, and how many times it's covering the diameter? 1 2 3 4 5 6 7. So just one higher, so it is nb plus 1, and in each movement it's covering the total shell diameter. So nb plus 1 into ds, where ds is the shell diameter itself, right. So there are empirical charts and all by which we can calculate the shell diameter for ff, right. So ff we can calculate from the Reynolds number, Re shell, which is dh into gs divided by mu s. So once we get this, dh has been already calculated, we have discussed about it, and dh is the hydraulic diameter of the shell. The same equation which we have solved for square pitch and triangular pitch will be used here, and from there we can calculate the shell side pressure drop. Okay. So that's all about the process design considerations. So in the next session we will initially discuss what are the stepwise design procedure of the shell and tube heat exchanger, and after that in the last session of heat transfer we will discuss some general problems. Thank you.